we can do that with the other derivation as well. Let's do that as an exercise. Okay, let's do that. So I want to do this with the definition, with the different definition of mutual information, which is h of x minus h of x given y. So let's do that with this one. And then I immediately note that this is h of pi. And all I have to figure out is what this h of x given y is. Okay, so writing the probability one more time for y, we note that this is pi times 1 minus p. This is pi times p, 1 minus pi times p. So this is p. And this one is 1 minus pi minus p. One more time. Okay. So this one has 3 cases. The first case is p y is equal to 0 times entropy on x given y is equal to 0 plus p y is equal to 1, y is equal to entropy on y is equal to 1, and py is equal to, sorry about that. It's okay. Py is equal to erasure times entropy on x, y is equal to erasure. So we need to add these 3. So let's figure out each one, each entropy. So what is entropy on x given y is equal to 0? So when you receive this, do you have any uncertainty on x? No. When y is equal to 0, input random variable x has to be equal to 0. There is no other way. So there is no uncertainty on x. Surely x is equal to 0 when y is equal to 0. So this is 0. What about entropy on x? Y is equal to 1. Due to the same reason, there is no uncertainty. So this part is 0. So you don't have to worry about these first 2. So what's left is this third term. So the third term is probability y is equal to e, which is p. And entropy on input given y is equal to e. Entropy on input is just h of pi. So what you get immediately is this expression maximize with respect to pi, entropy of pi. The second part is p times entropy of pi. So this is again max 1 minus p times entropy of pi. That is, so this can be upper bounded by 1, and the equality is achieved with pi is equal to half. That is nothing but 1 minus p. So we have 2 different ways to prove the capacity of binary erasure channel is equal to 1 minus p. What is the physical meaning of this result? Binary erasure channel, you have lost this much information, let's say with the probability P. So when you send something at the transmitter with a probability P, that information is lost. That cannot be recovered. So the capacity is the total information that you send at the transmitter and take away the amount of information that you lost sending information across the channel. So it cannot be revived. What's lost can be revived. Okay, revived. So the capacity is 1 minus P. Makes sense. Okay, so that's the binary erasure channel. The capacity of a binary erasure channel. Having said this, what will be the interpretation of binary symmetric channel capacity? The binary symmetric channel capacity, when we compare with the binary erasure channel, so binary erasure channel capacity minus P, capacity of binary symmetric channel where we have overlaps, minus of HP. Okay. So when we take a look at the curve for H of P look like this. P is equal to half, it is maximum, which is equal to 1. Okay, so when we compare the capacity, let's say P is equal to, let's say, 1 over 10, something like that. It will be somewhere around 0.45. In the ballpark, let's say just is half. Then this, if P is equal to 1 over 10, this is around 0.55. What about this one? This is 1 minus 1 over 10. So this is 9 over 10. As you can see, this one is much bigger than this one. Because the binary symmetric channel, it is much more confusing because this crossover probability, this crossover event, you send the 0, it could be 0, it could be also 1. You send 1, it could be also 0 or 1. So this channel is much more complex channel. That's why the capacity gets smaller. All right, so that's a little bit of interpretation, physical interpretation of these two channels, which are very important. Today we have coding theorems, coding schemes that achieve the capacity of binary erasure channel. It has been proved to be using LDPC code, some coding scheme, which is low density parity check code. And also we have LDPC code approaching this capacity infinitesimally small. Approaching this capacity with the infinitesimally small difference. So we consider this problem has been solved. Finding the coding scheme that approach this capacity very closely has been found. LDPC code, one of them is low density parity check code. Probably we will talk about LDPC code a little bit within this semester.